Okay, so the fourth section from chapter 2 here, I'm going to try to go through these relatively quick here because we've actually seen these before in a lot of detail, so hopefully this section is pretty easy. But anyway, we've talked about relative motion before. If two objects are moving towards each other, keep in mind when we have that situation, right, if I have two objects that are going towards each other, and I want to know what is their relative motion with respect to one another, then I would actually sum those two vectors, right? If those two vectors aren't acting on the same object, if this is person 1 and this is person 2, and I want to know how fast is person 1 moving with respect to person 2, I would actually add those two vectors up and I would say that they're moving at 25 meters per second or whatever those units may be with respect to each other, right? What if two objects are moving in the same direction? Well, that's where it's maybe a little bit easier, right? If object 1 is moving this way at 10 meters per second, and object 2 is only moving this way at 5 meters per second, then object 1 is moving 5 meters per second faster than object 2, and so it would be moving 5 meters per second relative to object 2. So again, this is really all we're going to look at in this section. Nothing too crazy here. So then the first example is about the most elaborate example I could think to make for all of this simple linear motion here. Right, so we've got a variety of different situations. So for part A, and obviously if you need to pause it and read through this, please do, but I'll go through it pretty quickly. For part A, you've got the car traveling after the bandits at 50 meters per second. The bandits are traveling at 55 meters per second. So how fast are the bandits moving with respect to the police car? Well, again, since they're going the same direction, the bandits are moving 5 meters per second, and I'll define that as a positive 5 meters per second with respect to the police car. If the police officers fire a bullet towards the bandit and the bullet leaves the gun with a 300 meter per second velocity, how fast is the bullet leaving with respect to the bandits? Well, we already knew that the bandits were going 5 meters per second faster than the police car, but now the bullet's being fired at that with 300 meters per second, right? So the bullet then is actually moving 295 meters per second towards the bandits. So how fast is the bullet moving relative to the bandits? Well, again, it's moving positive 295 meters per second towards the bandits. Part C, how fast is the bullet moving with respect to an innocent civilian who's just standing on the sidelines and watching this? Well, again, the police car is moving at 50 meters per second, and then they launch the bullet there, which moves an additional 300 meters per second. And so the civilian would just notice the sum of those two because he'd be witnessing the car and then the bullet's velocity on top of that. So it would appear to be going 350 meters per second in that same direction. And then part D, how fast is the bullet moving with respect to you if you're driving down the opposite side of the highway at a speed of 35 meters per second? Well, again, really what I would do for this then, for part D, I know that the bullet is moving with respect to a stationary person at 350 meters per second, but we're not stationary, we're actually going the opposite direction here. So then we're moving at 35 meters per second this way. Well, again, I'm just going to sum those two vectors up because they're moving opposite of each other, right? And so the relative motion between them is actually 385 meters per second. And it'd be 385 meters per second away from you, right? As it moves in the other direction and you move towards it. But anyway, very, very simple example, hopefully, that illustrates about every combination we could see. Sometimes they're moving towards each other, sometimes they're moving away from each other, sometimes you have a third-party observer that's not actually moving at all. But make sure you are very comfortable with the basics here of relative motion. This next slide here, the Galilean transformation of velocity, it's a general rule for finding the velocity of an object with respect to multiple observers. It looks kind of confusing, it looks way worse than it actually is. Because really all this is saying is exactly what we just did. Let's start by this definition, right? This definition is saying the position from C to B, the position, or I guess I should say from B to C really, is equal to the sum of those two vectors, right? Going from either B to A and then A to C or vice versa. So adding those two vectors up gives me the resultant that is RCB as they've defined it over here. Right, so this is nothing too crazy. This can just be observed from the picture over here, right? The next expression down here is just saying if we do the derivative of each of those with respect to time, well, if I take the derivative of the position with respect to time, then really all I get is the velocity, right? So what this is saying is then the velocity from B to C would be equal to the velocity vector from B to A, or A to B, and I guess I'll stay consistent with the order, so from C to A I should say, plus the velocity from, here's my A to B. So all this is saying is if I do the derivative with the position with respect to time, I simply get the resultant being the velocities. And again, this is basically what we just said. All it's saying is we could actually extend that then to 2 dimensions instead of just 1. But we just did this example basically in our first example a moment ago. Okay, so don't be thrown off if you see some notation that looks like this. It's really the exact same thing we've been doing. It just elaborates that we can do it in 2 dimensions as well as 1. So then a relatively easy example to illustrate this, right? So Cleveland is 300 miles east of Chicago. Plane leaves leaves Chicago flying due east at 500 miles per hour. But the pilot here forgot to check the weather and doesn't know that the wind is blowing to the south. So the pilot's trying to fly directly to the east, but the wind is actually blowing to the south, and therefore we know the resultant would actually be right south of east a little bit. Okay, so 500 miles per hour is how fast the pilot is trying to go this way. The wind is blowing south 50 miles per hour. What is the plane's ground speed? Well, in order to find the plane's ground speed, we simply need to find the hypotenuse, right? As a casual observer on the ground, we wouldn't notice that they're flying east and south. We would just see the actual resultant, which is south of east, I should say. So anyway, again, all we have to do then is calculate that hypotenuse. So the ground speed then of the plane ends up being about 502.5, about 503 miles per hour. And again, that's how fast the plane looks like it's actually moving. So there's my answer to the first part of this question. And then they ask, where is the plane 0.60 hours later when the pilot expects to be landing in Cleveland? Well, again, 0.60 hours later, if we look at really just the components of this, right, the reason he's expecting to have landed in Cleveland is 500 times that would give me 300 miles, which means he will in fact have gone 300 miles to the east. And so the pilot actually will be over 300 miles to the east, but the problem is, since he's also being blown south, right, he'll also have gone 50 miles per hour times that 0.60 hours south. So if we actually then calculate that, if we calculate 0.60 times 50, we figure out that the pilot is actually then 30 miles south of Cleveland. So he actually flew the right horizontal distance, right, but he ended up being south of where he was aiming. So anyway, he ends up 30 miles directly south of Cleveland. And it is worth noting that he's directly south and he's not over here somewhere right off at an angle. He is directly south of the city. So in the quick follow-up then to that second example, we have a smarter pilot who this time is flying from Chicago to Cleveland, but actually wants to fly directly east, and so she's going to account for it by directing her plane slightly north of east. How long does it take her to reach Cleveland, and which angle must she fly at? So the plane speed is still the same. It's still the same plane, which means the plane can only fly at 500 miles per hour. However, the wind is still blowing to the south at 50 miles per hour. And so what that tells us then is the actual resultant, the actual ground speed, if you will, of the plane is actually going to be less than the original 500 miles per hour. Right? Some of her velocity is being used to counteract that of the wind there. So anyway, when we calculate this number, and if you notice that I was pausing there, it was because I was calculating this number, it ends up being about 497.5 miles per hour. So again, this is the actual resultant. This is how fast it looks like she's flying. So yes, she is going a little bit slower than the aircraft is actually traveling. However, she is going directly in line with where she wants to go. So for the first part of this question, they actually just asked us what was the direction she needed to fly. And to do that is a simple little bit of trig here. So if I just use those original measurements and I find my angle, right, all I have to do then is the tangent inverse, or not tangent inverse, excuse me, the sine inverse of 50 over 500. And again, calculating that number, it ends up being about, so theta ends up being about 5.74 degrees north of east, right? So that's not in terms of bearings, this is just in terms of direction, north of east. If I was doing north, it would be the complement of that, so north 84.26, I guess, east. Anyway, so I've got the direction. But then for the second part, how long does it take to reach the black hole of Homestead Dreams, that is Cleveland? Well, I know that she's traveling at 497.5 miles per hour, and again, going back to that previous problem, it was 300 miles away. So I simply use velocity equals delta x over t, and I solve for t. So 300 miles away, and then the 497.5, it's going to be very, very close to the 0.60 hours, right? So again, just solving this, it ends up being about 0.603 if you prefer 3 sig figs, but 0.603 hours to reach Cleveland. Okay, so anyway, we've got those two measurements. Again, hopefully a pretty easy problem to set up and solve. Okay, so a real quick check then. A plane is traveling horizontally to the right at 100 meters per second. It flies past a helicopter that is going straight up. So the plane's going this way, 100 meters per second. The helicopter is traveling straight up at 20 meters per second. From the helicopter's perspective, and obviously it's very important we know what we're relative to, what is the plane's direction and speed? Okay, so as the helicopter is going up, right, the plane still looks like it's moving to the right, but as the helicopter goes up, it actually looks like the plane, right, is dropping down towards the helicopter. So the plane's resultant then, with respect to the helicopter, ends up looking like it's going to the right and down. So it's going to the right and down, so I can rule out a lot of those options. Right and up, all of those can go away. And then the resultant, well, the resultant would be more than the 100, right? Because we're going 100 to the right, plus it looks like it's going 20 meters per second downward. So then the resultant would be the hypotenuse of those two, which would obviously be more than 100. So looking at this, F is my best option here. It is not exactly 100, and it is not less than 100 because the vertical vector here is adding to the horizontal vector. They are not working against each other in any way, shape, or form. So even though this question here, as you read through it, you notice that everything's left in terms of variables, no specific measurements are given, I hope that you guys agree it's still a pretty easy question as long as we take the time to set it up. So they give us all the measurements. The beltway there is moving at V1. It's a length of L. The woman is standing on it. A guy is walking on it. What time interval is required for the woman to travel the distance L? Well, again, the woman is just standing on it, so she's moving at a velocity of V1. She needs to go a distance of L, and we want to know how long it took her, so it's a simple, she's moving at a constant velocity. So if I just solve that for t, I would get L over V1. Right, so the woman's velocity, the woman's time is not very tough to find. Part B hopefully is also pretty easy, although it is a little bit trickier, right? But anyway, for part B, they say what time interval is required for the man to travel that distance. Well, the guy was on the beltway, which was moving V1, but he was also walking then at a speed of V2. So his total speed with respect to the distance L, that is a stationary distance, right? His total speed then is V1 plus V2. So that is his resulting velocity. He still needs to travel that same distance of L, so if I want to find the time for him, again, I just set this up, and then I solve for t. So the time for the guy, so this was the woman, this was the guy, the time for the guy is L divided by V1 plus V2, which obviously should be a little bit less, right? But if I'm adding to the denominator, it's going to end up being a little bit less. So then for the third and final part of this question, right, just to have a little bit more fun, a second beltway located adjacent to the first one is moving the opposite direction at the same speed. The instant the man steps onto the beltway, a lost child steps onto the one adjacent and stands at rest relative to the beltway. How long after stepping onto the beltway does the man pass and ignore this poor lost child? Right, so again, what's happening here? We've got the guy stepping on the beltway at one point. We know the total distance here is L. We know that the guy's total velocity was V1 plus V2. We have the kid stepping on the opposite beltway, moving the opposite direction at V1, and so I want to know how long does it take for them to pass. Well, the good news here is whenever they pass each other, they've traveled a total distance still of L, right? If this ends up being whatever x, then this would be L minus x, so the total distance would still be L. So my total velocity, because they're moving opposite each other, would be V1 plus V2 plus another V1 from the child. Total distance is still L, and then the time is t. So simply solving for that time, I get L over 2V1 plus V2. And that's all there is to it. Again, hopefully this wasn't too bad to get through.